Yes, and we're going to have a lot more quizzes than that. Functions. Because this time in this section, we're dealing with functions and their graphs. What is a function? What does a function look like? What? Yeah, because basically we're used to doing this. And I give you an X. Functions are now written this way. The equation part's the same. It's just instead of saying Y, I'm saying this is a function, the name of the function, and this is the variable. So anywhere I see this, it goes in place of the variable. Functions that with respect to equations will look like this, where that's the name of the function, and this is the variable in the equation. So anything I put inside the parenthesis, will replace whatever that value is in the equation. So that's what the equation part of the function looks like. But now the definition of a function. Is the correspondence of the first value called the domain to one and only one value in the range. We have an ordered pair, and it matches, let's say, to a specific location. The first element is the domain. There's your X values. The second value is the range. And what does one and only one value? What does one and only one mean? One and only one means that each X value can have only one Y value associated to it. And instead of associated, up on top, we use the word has only one corresponding to it. What does corresponding mean? Have you ever heard that word before? Where have you heard it? What did it mean in the old days? What does correspondence refer to? Before there was distance education like we know it today, it used to be called correspondence learning. Well, what happened is the instructor would mail the student the assignments. The students would work it out and mail it back to the teacher. That's correspondence learning. Now, the reason they use correspondence, can you mail the same letter to two different people? No, it won't be the same, because if you make a copy of it, it's no longer the same. It's a copy of it. Can you send the exact same letter to two people at one time? No. Here you have your X values, which we call the domain. Let's call it A, B, and C. And here are our Y values, which we call the range. It goes to 1, 2, 3. We call this a mapping. Is that a one-to-one correspondence? Does each member of the X value map to one and only one member in the Y value? Yes. Is that a correspondence? Is that a one-to-one correspondence? Yes, it is. Look what it said. One-to-one correspondence says what? Each X value corresponds to one and only one Y value. Are all the X values mapping to one and only one Y value? That could be the same one. Think of a classroom. The students and the instructor. All the students give the instructor their work. That's a one-to-one correspondence. So that's a correspondence. And for one-to-one, we short script it that way. This is a one-to-one correspondence. Is that a one-to-one correspondence? Yeah. Is that a one-to-one correspondence? What's the difference between that one and all the other ones? Right. So basically, what you're just noticing that out of each of the domain values, there can only be one line going out of it. Each of the domain, each of the X values can only have one Y value associated. Is that a correspondence? Yeah, but all you have to look at is look at the X values, the domain values. Is there only one line going out of them? If there's only one line going out of them, then it doesn't matter where they go to. It is a correspondence. Is that a correspondence? You tell me why it is. Yeah. A is going to the same one. As long as it's going to the same one, it doesn't matter how many times it appears. That was a trick question. Now let's look at what's called a relation. A relation is a correspondence between a first set, the domain, and a second set called the range, such that each member of the domain corresponds to at least one member of the range. A relation is a correspondence between the first set of the domain and a second set, the range, such that each member of the domain corresponds to at least one member of the range. So, is it one-to-one? What does one-to-one mean? One from the domain to one and only one in the range. Is this one-to-one? At least one. No, this is not a one-to-one. Because this one says at least one, which at least one could be 2 or 5 or 7 or 12. It's not one-to-one. A relation is not one-to-one. So here's the example. Is this is it asking for a relation? Determine whether each of the following relation is a function. Identify the domain and range. So is this a function? If so, tell me the domain and range. What's the difference between a function and a relation? Which one's one to one? A function. A function is one to one. A relation is one to at least one. So is this a function or a relation? Yeah, because if you have the same x values, and the y's are different, it's not a function, it is a relation. Because one to one is function, one to many is a relation. A function is one to one. What does one to one mean? Each x goes to one and only one y. That's what one to one means. A relation is one to at least one. Okay, here's semantics. Can a relation be a function? When? When it's one to one. But once it goes to 1 to 2, 1 to 3, then it's just a relation. Yeah, it's just all semantics. The next one. -2, 5. 5, 7. 0, 1. 4, -2. Is this a function? First off, is it a relation? Yeah, that's pretty much safe to say yes. Is it a function? How can we tell? What's the easiest thing we look at here to say it is a function? Well, if we look at all the x's, if all the x's are different, automatically it's a function. If all x's are different, then automatically it's a function. So it's a function. And it's also a relation because it can be one to one and one to many. -5, 3. 0, 3. 6, 3. Is this a function? Why? All the x's are unique. All the x's are different. So it's automatically a function. Does it matter if all the y's go to all the y values are 3? No, because we're just looking at all the x's going to different y's. Each x has to be unique. How about this one? Is this one a function? If I give you time to think about it, you're going to change your answer. Is it a function? Why?
2, 5 is the same number.
Yes, these are the same points. So this is a function. Since these are the same, this x and this x go to the same value, it's the same number. So that all the x's are different. You're just looking at just the x's being the same. If the x's are the same, the y's better be the same. Trick question. So this one is a function. You got it now? Put it into words. Put it this way, is if the x values are the same, the y values must be the same. Because if x and y are both the same, then it's the same point. So it is a function. So numerically, it's pretty, you have to do a lot of thinking. How about graphically? What would it look like if it was graphs? If you had graphs, what would a function have to look like? What would have to be true about a function? What about the graph is true for functions? These are all functions we're going to look at. We're going to talk about these a lot in the next couple of days. Is this a function?
No.
Yeah, no. Is this one a function? I want to say, firstly, which ones do you think are for sure? Is this a function? Is this one a function? Is this one a function? You say no. ¿Por qué no? Why not? Well, if I do this one, is that one a function now? This one is a function. Both of these are functions, actually. This one is a function. This one is a function. This one is not. This one is. This one is not. Now, let's look at what they have similar to each other that they are and they aren't. What's
It's crossing the y twice.
Well, that's true. That's one. Yes. That's one thing you look for. A function can only cross the y value 1 point. So that's not because it crosses it twice. This one's not because it crosses it 3 times. And it's not just because it's the y-axis. Very good observation there. The reason these two are not functions, what kind of line is the y-axis? Which direction is it going? Is it horizontal or vertical? It's a vertical line. So in other words, if I give you this, is that a function? Why not? This is a function. This is a function. This is not. It has to do with what the y-axis looks like. It goes up and down. It's a vertical line, right? If you can draw a vertical line anywhere on the graph and it crosses it more than once, it's not a function. Yes, it's called the vertical line test. If you can draw a vertical line anywhere on the graph, and it crosses more than once, it is not a function. If you can draw a vertical line anywhere on the graph and it crosses it more than once, it's not a function. It's called the vertical line test. Think about it. On this graph, if let's say this was 5 and this was -3, what's the location of this point here? 0, 5. What's the location of this point here? X's are the same, Y's are different. So if we put it that way, it makes more sense. So that's what we're saying. If you can draw a vertical line anywhere, it has the same X's, but different Y values. And that's what happens. That's what it looks like. So if you can draw a vertical line anywhere on the graph and it crosses more than once, it is not a function. So let's look about equations as functions. Or here's our function. Given f of x is equal to 2x squared minus x plus 3, find the following. Let's make it -2. So in this first one, A. So this is the name of the function. So we look for it. It's defined here. So this is what it means. It means 2x squared minus x plus 3. Notice what's inside the parentheses is what? The x. In this case, it's in the function, it's x. I changed x to 0. So anywhere I see an x, I put a 0. So that becomes 0, that's 0, so the answer is 3. So f of 0 is 3. That's how you read functions. let's say we had this equation. The way you would read this is the function f of variable x is equal to 3x plus 2. That's how you'd read it. But we don't have to read all these words in there. The way we would normally read it is f of x is 3x plus 2. That's how we would normally read it. Because that's the name of the function of this variable is this equation. So it makes it much easier to read that way. So how would you read this? F of 0 is 3, equals 3. This one, f of 0 is 3. That's how you'd read it. B says f of negative 2. So whatever's after the word of, that defines your x value, f of negative 2. So anywhere I see in my equation, anywhere I see an x, I put a negative 2 in its place. So anywhere I see an x, I put a negative 2 in its place. The order of operations, what do we do first? Can we do anything inside the parentheses? No. Can we do any exponents or square roots or anything? Yes, here's an exponent right here. So negative 2 squared means what? Negative 2 squared means negative 2 times negative 2, which is positive 4. So it's 2 times positive 4. Negative times negative is a positive. Two times 4 is 8. 8 plus 2 is 10, plus 2 is 12. There's your answer. Remind me, let's go, after we finish these examples, we'll go through all the examples of exponents.
How about 3 plus 3? In the top one?
Oh, this one?
Yeah, unless you changed.
I changed it. It was a misprint. There. I just instead of 2, put, thank you. Thanks for catching it. I don't know why I like writing 2s. Okay, C says f of 5a. So it's 2 times 5a squared minus 5a plus 3. So what do we do? We can't do anything inside the parentheses. What do we do with this one? The rule here, we have 5a squared, which means it's 5a times 5a. 5 times 5 is 25. A times a is a squared. We could have done it like that, Or what this actually tells us also is we can take this, since these are multiplied, I can distribute it inside there. So it's 5 squared a squared, which is 25 a squared. So this one says it's 2 times 25 a squared. Negative times positive is negative. 5a plus 3. 2 times 25 is 50. A squared minus 5a plus 3. And there's your answer. And D. This is f of a minus 4. F of x is 2x squared minus x plus 3. Yeah. So anywhere I see an x, I put this equation. So it's 2a minus 4 squared minus a minus 4 plus 3. So anywhere I see an x, I put the a minus 4. I don't know why this is chapter 1 and they're making you do the quadratic stuff already. I don't know why the authors chose this, but let's look at this. What do we do with this one? A minus 4 squared means a minus 4 times a minus 4. And we have to distribute. What do you call it? A starch foil. Yeah, since it's binomials. So a times a is a squared. Positive times negative is negative. A times 4 is 4a. That's it for that one. Negative times positive is negative. 4 times a is 4a. Negative times negative is positive. 4 times 4 is 16. So everything in the first parenthesis has to multiply to everything inside the second. That's why we have 2 there. 2 times 2 is 4 terms. Whenever you get rid of parentheses, first step, always combine like terms. So we have negative 4a minus 4a. They're both negative. So we add the numbers. 4 plus 4 is 8a. And we're going to spend a lot of time discussing this later on in this course, chapter 3. But they threw it in chapter 1. I don't know why. So this gives us a minus 4 squared becomes a squared minus 8a plus 16 minus a minus 4 plus 3. All I did with this so far. Now what do I do? Well, yeah, and since we can't do anything inside the parentheses, we get rid of the parentheses. Yeah, so you distribute the 2. 2 times a squared is 2a squared. Positive times negative is negative. 2 times 8 is 16a. Positive times positive is positive. 2 times 16 is 32. Remember, treat the numbers and the signs separately. Negative times positive is negative a. Negative times negative is positive 4 plus 3. All the parentheses are gone. So we do what next? Whenever you get rid of parentheses, always combine like terms. So the term for the a squares, we only have two of those, a squared. How many a's do we have? We have negative 16 here and negative 1 there. So negative 16, negative 1, they're both negative. Add the numbers. 16 plus 1 is 7. Then the integers. They're all positive, so the answer is going to be positive. 32 plus 4 is 36. 36 plus 3 is 39. There's that answer. Lot of writing. Example 5, we're going to skip for right now. Because what it's saying is graph these functions. We're going to do all these when we do something called transformations, which is the end of next chapter. But I can tell you that this graph will look like this. This one will look like that. And that one will look like that. But we first have to talk about what the functions are, what the basic functions are, and then we'll do those. We talked about vertical line test. Vertical line test. This a function? 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 Yeah, because notice at -1, that's a solid circle and that's an open circle. What's the difference between a solid and an open circle? Yeah, solid means you can count that one. Open means you can't use that one. So for the -1 line, even if you draw a vertical line, that's the only one that counts. So far, so good? Well, we're gonna do the ranges later on, perhaps. We're gonna do domains of functions in this one. Again, what are domains? The x values. So by domain of functions, we're gonna the list of all possible x values that can be used in a function. Note the only x values that we cannot use are the ones that do what? What are the only x values we can't use? What? Nope. The only x values that we cannot use are the ones that make the function undefined. So the only x values that we cannot use are the ones that will violate the rules of math. Again, this will become a lot easier once we discuss the library of functions. Example 8. Here's the first one. Here's f of x. I'm going to expand this a little bit. So find f of 1 and f of 3. So what's f of 1 going to give me? What do I do with 1? Where? In place of x. So 1 minus 3 is what? Here's the rule. If you have two numbers and they have opposite signs, take the sign of the larger number. So we know since 3 is bigger than 1, it's negative. So the answer is going to be negative. If the signs are different, take the sign of the larger and subtract the numbers. 3 minus 1 is 2. So the answer is -1/2. And the negative always goes either in front of the whole thing or on top. You never want the negative on the bottom. So is 1 in the domain? Is 1 in the domain of x? Yeah, because it's not an invalid answer. How about 3? 1 divided by 3 minus 3. 3 minus 3 is, what is 1 over 0? Undefined. You cannot divide by 3. So 3 is not in the domain of x. This causes most trouble and a lot of trouble with students. If the 0 is on top, what does that equal? If the 0 is on the bottom, which I'll say does not exist. Why is that? Why is the position of 0 that important? Look at what the statement says. How many times does 3 go into 0? 0. It doesn't go in there. But how many times does 0 go into 3? Infinite many. How many ways can I give you nothing? Infinitely ways. I promise to give you nothing for Christmas forever. So if 0 is in the bottom, 0 goes into 3 infinite number of times. So it's undefined. 3 goes into 0 no times. 0 times. So that's the difference between the two. All right. B. F, or in this case, g of x is equal to radical x plus 5. Find g of 16 and g of negative 7. So g of 16. Anywhere I see an x, I put a 16. Square root of 16 is 4 plus 5. So is 16 in the domain of x? Yes. In the domain of x. B, g of negative 7. The square root of negative 7. What's the square root of, instead of 7, I'm going to put negative 9. Make it easier for us. What's the square root of negative 9? Remember, what is square root? Why is it, what is square root of 16? Why is that? Because, yes, because the same number, 4 times 4 equals 16. Can you do the same thing with negative 9? No, because if it was negative 3 times negative 3, it would equal positive 9. If it's positive 3, it's positive 9. So you cannot take a negative inside a radical. So it does not exist. Negative 9 is not in the domain of x. Again, and number 9, we can't do it because we haven't learned the functions yet. Well, actually, we could do this one. Example 9. Find the domain of this function. F of x is equal to 1x minus 7. What's the domain of that one? What's the domain of this one? Whenever you're asked a domain, questions to ask. Here's the first one. Are there any x values that would make, what can we not have in a fraction? What can we not have in a fraction? In a fraction, you cannot have 0 on the bottom. So, are there any x values that would make 0 on the bottom? Yeah, so take this equation, x minus 7 equals 0. So because 7 would make it 0, we cannot use that. So our domain is any x except 7. That's our domain. And we can't do any more examples. But I'll show you why. It wants you to graph these functions without a calculator. Yeah. You haven't learned these functions yet. So we'll do these when we finish next chapter. Other than that, that's all we can do in this section. End of section 2. And I don't want to start the next one.